Again, let me introduce you Michael Gibbs. Michael graduated in computer science and mathematics from Nottingham Trent University, and currently he is a PhD student in his final year in the Smart Sensing Lab. He is going to present the work entitled Hard Contextual Parameter Sharing, a Multitask Learning Approach for Tiny Machine Learning. Please.
Hello. Good morning, everyone. I just want to first sort of outline what we're going to do today. I'm hoping to kind of take you through a bit of a journey of this work, starting from kind of the idea generation all the way through to deployment, with a little bit of an example to help you kind of understand exactly what we're doing here for those even who aren't experts in the field. So this is my third time at the EMEA, and last year I presented a poster. I'm just going to kind of remind of that work. So we use two deep learning models to contextualize data using, so one model contextualizes information for the main model using human activity recognition and stress. Okay? And what we found was combined we had a model size of 1.3 megabytes, but the activity recognition model had to be very small. So it kind of there was a big trade-off between having multiple models housed on one microcontroller. So this need for multiple models on a microcontroller is going to be, I think, more useful in the future. Okay? Because imagine your mobile phone. Okay, there's a lot of software on your mobile phone. There's a lot of things your phone does. So it's not crazy to think that in the future we're going to need microcontrollers to kind of start adopting the same thing and do multiple tasks on one device. And there's actually a strand of research that kind of follows this called multitask learning, but I'll talk a bit more about that later. So hard contextual parameter sharing is a new way of trying to reduce redundancy on microcontrollers and do so in a way that doesn't stress the hardware. So to try and group things together in a nicer fashion, kind of similar to the last talk, but in a bit more of a harder sense, I suppose. So I've just got a quick brief example just to help everyone understand exactly the process. So I've got three sentences here. Sentence one, the aim of the sentence is to exemplify the idea of HCPS. Sentence two, the aim of this sentence is to say I'm having a lot of fun here in Milan, which I am. And sentence three is the aim of the sentence is to be very different from the other sentence and talk about a dog. Okay? So there are three very different sentences, but they all have these shared components. So instead of having these written 3 times over, why don't we split these up into shared components and individual differences? So if we just quickly reflect on that process, we reviewed our sentences, we identified some key similarities, we copied the similar information and split them up, and we reduced the original sentences so that we have the shared and the individual differences. Okay? Now if we highlight the word sentences and change that to models, it's almost exactly the same. And this diagram on the right there is going to sort of help and is color-coded so that as we go through a more technical example, you can see exactly where we are in the process. So more specifically, if we kind of take it more mathematically, for some selection of n models, I've got an example of n equals 2 at the bottom for if you want more of a visual representation. If we have a vector of models, we'll call that M. We can sort of reduce that using HCPS to create M bar. And that will contain, instead of these full-size models, it will contain the reduced models as well as the shared component S. Okay, you can kind of see those highlighted there. Those reduced models M, highlighted in yellow, and the shared component has been copied in. And the main idea is to have M bar be less than the size of M. So that's to say that we're reducing the overall size of the model or of the system by introducing this method. So how do we identify the shared component? That's quite a tricky task. So the shared component is just some initial subset of one of the previous models, in this case, where we can say that it is the first J layers of some network alpha in our original model vector. Now, there is a slight limitation here. It is very tricky to find these parameters alpha and j, much like when you're training any neural network. It's difficult to find the exact components that you need, the exact hyperparameters. This is another sort of issue. But I thought it'd be fair to highlight these as we go through. So next, we want to copy, once we've found the shared component, we want to copy this shared component into all of the other networks. So if we had 3 networks, we would copy whatever our shared component is into the first J layers of network 1, 2, and 3. But we need to remember to do a single pass of training, or however many passes of training as you like, so that the layers agree with each other. Okay? And finally, use your imagination real quick and pretend that the bottom diagram is still the bottom diagram. Now all the models are reduced, now all the models are trained, we can remove the shared component from the other models just to leave the individual differences. So we've got just the shared model and the individual differences like we had in M-bar previously. So I mentioned hard parameter share, I mentioned multitask learning earlier, and a subset of multitask learning is hard parameter sharing, as seen on the left there. So how does this differ from hard parameter sharing? You can see that this is hard contextual parameter sharing. So we've added in the individual contextual component because hard parameter sharing runs all individual tasks all the time, and it's not feasible to do this on a microcontroller as it stands. So by adding in the contextual condition, you're gating off the need to run all models, and you want to run just one. Much like from the work we did last year, that contextual condition could be another model itself. So it could be something like activity recognition. Okay? Just as well, another main benefit of this work as well is if you have the shared model and you want to add a new class in, you don't have to retrain the entire model again, having to introduce this new introducing this new class into the entire model, nor do you have to train an entirely new model and try and bolt that in. You can use the shared model and train a new model and kind of add in just the individual difference model, this nicely reduced model at the end. So we applied this onto the Arduino Porcenta H7. You can see just some of the basic specs there. We've used this microcontroller purely because of compatibility. I've had some work previously just about issues with compatibility and things like this, and these not so obvious issues. And we also used the vision shield because we did a visual classification task, a image classification task, and we combined them together to overall get this system here. We classified these 2 data sets, the MNIST data set and MNIST fashion. MNIST is a very well-known benchmarking data set with digits 0 to 9, and the MNIST fashion data set is fundamentally different, while similar enough to still share some individual components, okay? And this classifies different items of clothing. But ultimately, these are 2 similar data sets that should still have some shared components. So our network architecture, we have just a very basic architecture just there. But an important thing to note about the architecture is we can only share parameters left of that orange line, because if we share the final layer, then we'll actually be losing all of the individual differences entirely, because that's where the softmax layer is. That's where if you're going to have entirely shared components, which may be unlikely in some cases, you won't have, if you share that last layer, you will lose everything. So these are our results. I first want to draw your attention to this first column here. You can see that the number of parameters decreases only when we get to that fifth dense layer, which kind of makes sense because of our 2D convolutional layer, and every layer in between is sort of doesn't actually have any extra parameters. But you can see the parameters is almost halved. You can also see that the accuracies don't really change when the shared model goes into the MNIST model, and that is purely because in this case our shared layers are from the original MNIST model. We did try it the other way around as well by having our shared model be the MNIST fashion sort of initial layers, but it didn't work out quite as well. We found that when we plugged our shared model into our MNIST fashion model, so the initial layers from the original MNIST model into the MNIST fashion model, you can see that the accuracies start to fluctuate a little bit more, and we found that when we shared 5 layers, we got a 49% reduction in parameters while having a 14% accuracy sacrifice. This could be fairly significant, and it varies application by application. Realistically, 14% might be too much for some applications, and 49% reduction in parameters may be generous. But even still, by sharing these components, you can still potentially save a fairly large percentage of storage burden. So we deployed it on the Vision Shield, and we just had a couple of small challenges. The Vision Shield resolution on the small camera is 32 by 32, and therefore needs resizing to 28 by 28. I just like to mention this because a lot of the times the pre-processing goes without mention in some of these. And the model switching contextual component was actually simulated using a button press. So again, this could be a separate deep learning model, but just for the sake of simulation, just with a button press. And consistently with our table from the previous slide, you can see that there's a 49% reduction in the model size, taking the model header file size. So where does this work go in the future? Okay, and what are the real challenges? I mentioned 1 or 2 on the way through. So the identification of shared layers is really tricky, and it's not always obvious. But for these small models, it's quite straightforward to just trial and error, much like when you're training some deep learning models. But as the models get large, you might want to introduce some architectural search or something else to reduce that time frame. The models themselves have to be the same architecture for now. I am working on something so that you can kind of get around that problem. But for the sake of this work now, the models have to be of the same architecture to share the layers across because of the matrix dimensions. They don't agree otherwise. And also, pre-processing is a fairly significant challenge. Yeah, so in the future, I'm just trying to focus on trying to share information so it's more forgiving to models of different architectures. So, in summary, today we've sort of recalled some of the previous work of using multiple models. We discussed why do we need multiple models. We introduced HCPS. So we followed the process in a general perspective from the sentences. We reflected on exactly what that process was. We then went into some more specific details. We identified a potential use case and followed that through the pipeline of the application, and then found a significant storage reduction in that case. Thank you.